Well, it looks like we can officially start. So welcome back, everyone. And congratulations, we got through the first exam. Those are always kind of stressful, especially the very first exam, since we have to kind of get used to what questions look like in an exam setting versus, say, homework or review problems. And once we do complete an exam, I'll always post this kind of information. So if you're curious about the summary statistics, you'll have that once everything's been graded. Let me pause for just a moment. And you can always find the solutions as well for the exams right after we've completed them. So it'll be the same answer key that I used to grade your exam. If you're curious on how any of the problems went, you can scroll through these and take a look. This one was not too bad. Folks did really well on this one. I think we were just kind of prepared for this. And as we should, that one was going to be kind of the trickier problem of the whole set, I'd say. So other announcements I want to make is I do have an interruption in my normal schedule. This was posted in the syllabus. I've known it for a while in advance, but because of that conflict of schedule, I won't have normal classes on our Thursday's class. So sorry about that, folks. We'll have a little bit of a break. I'm still going to hold office hours from 4 to 5 p.m. So if you come to room 220, just across the hall that way, that's where I'm going to still be. But then my interruption is really for the evening classes right after that. That means there's going to be kind of an interruption on assignment 3. It is officially due on Thursday, but I will accept it late. So I'll have the due date officially extended to September 18th. If you handed it in already, then good on you. If you want to work on it a little bit more, then you can have it back. I bring them with me to class. But we'll collect those officially on Monday when we come back. Does that sound all right to folks? Okay. And because this week is, again, really weird, Monday was the exam, there's an interruption with my schedule on Thursday. Assignment 4 is kind of a short and just a nice one. It's almost a freebie. It's only going to be based in section 3.2, so just those problems. So it's going to be kind of a easy week after we got through an exam. That's how it's always going to be, whether we have a Thursday class or not. I don't expect any further interruptions on my schedule, but after we have an exam, assignment's going to be just 1 or 2 sections. So we get a bit of a break. Other questions or comments at the moment? Okay. Also, one thing that can be confusing about my formatting here is when you go to take a look at the exam, you have 2 scores. Your first score is just a fraction out of the total possible points, which was 75 for this particular exam. And your second score is just your grade that you currently have in the class. If you go up to your grades right here, you'll see course score at the very top. And it's always going to be at the very top. I'll be updating that every time I grade an assignment or an additional exam. So I'd say double check on that, see how it changes with time. And I'll always have that posted. And the way I calculated your course score right here on the first exam was I went to the syllabus. I took 25% for just assignments number 1 and 2, since 3 was due on this Thursday. And the rest of this for exams, I weighted exam 1 as 75%. So that's a huge, huge weight. Exam 1 is just going to be 15% once we put in final grades. But that's just the way I try to get you a feel of how you're doing the class right now. Your exam grade is just exam 1, and your homework grade is just based off assignments 1 and 2. So if you're not happy with your grade, keep in mind, it's very, very minimal information going into it right now. Your grade has potential to change quite a lot. And last announcement, but any questions at the moment? Okay, last announcement I want to make is some of these exams are trickier than others. I mean, sometimes it's more just getting started. Chapter 2 is pretty hard for an introductory chapter in a new math class. And sometimes it might be other chapters that could be kind of a weak spot. But if you had one bad exam, in my opinion, that really should never hurt your grade. It shouldn't drop you even by a letter grade. And the way I account for that is every semester I do this class, I also put something that's not here. Oh, geez, where'd it go? I think I put it in the wrong course. That's kind of scary. Let me see if I can fix this real quick. I put it in a class, but I might have put it somewhere wrong. So it wasn't algebra. Where did it go? This is calculus, okay, and my other course would be statistics. Oh yeah, that's misplaced. So I'm gonna have to hide this before anyone sees it. So that's supposed to be on our class. I'm going to fix the Moodle website. And this is the extra credit opportunity. Again, if you just have an off day and you had a bad exam out of the 3 that we'll be having, and it drops your letter grade, try not to sweat it too much. Because if once you do your final exam, if you make up, say, that weak spot on, say, exam 2 or exam 3, wherever it happened to be, by scoring really well in the final exam, this is what will happen. Your final exam score, if it's higher than your minimum score amongst exams 1, 2, and 3, I'll replace your minimum score with your final exam score. So that'll be a full-on replacement. The other thing I should mention is I usually don't curve exams, but the final exam is the one exam I might curve, depending on how difficult it actually turned out to be. So if I do curve your exam grade, it is the curved grade that would replace the minimum amongst exams 1, 2, and 3. We'll probably talk about that more, but the punchline is don't let one exam get you down. It happens. It's happened to me. You can always pull through. And the final exam is your opportunity to make up any kind of bad exam. Well, any questions or comments at all, folks, so far? Okay, that was about 7 minutes of announcements. I should go back to the right class. And so what we're going to be doing today is taking a look at the product rule and the quotient rule. We're extending past the prior section when we looked at the power rule, we looked at the constant multiple rule, and so on. And so we're just building on what derivatives can we actually take. So let's take a look. In 3.2, there it is. That's the product rule. It's written in 2 ways. The way I have it displayed right here, that's Newton's prime notation. And what makes this a bona fide product rule is this. If you're multiplying 2 functions and you go to calculate the derivative, it's not the derivative of f times the derivative of g at all. And that's a huge, huge surprise. It feels like it should be, but it doesn't quite work out that way. The way this really should go is, let's just blow this up just a little bit more. If you're taking a derivative, so that's the prime there, then we go in order of differentiate one function and copy the other. Then go to the other function there, just copy it and differentiate the other function. So that's essentially the pattern of attack. If there's 2 functions, f and g, they go together in that particular way. Pay attention to the primes, the differentiation, because that's pretty much the whole game. If we wrote it out in Leibniz notation, it looks ugly and it's really the same kind of thing. Here's your f of x, it's just being copied right here. And this is the derivative of the g function. Now, it's a little bit weird because in Leibniz notation, it's written slightly in a different order than what's above here. But with plus, you can just change the terms. If they're multiplied, you can change the order of multiplication. And the reason Leibniz notation is written this way is if you put a differentiation operator, d by dx, same as a prime, typically you only put the thing you're differentiating to the right and the thing you're copying to the left, so there's no miscommunication. Pretty much that's the main reason it's written in this format. So going up to this term, here's the, well, I scribbled on it. Here's the differentiation operator, d by dx, function f, and function g. I'll typically always be doing this kind of problem. If I'm doing a product rule, I'm going to write it out in the prime notation like this. But if you like Leibniz, it's pretty much the same thing, just different looking. Any questions so far? Okay, before we just go and start differentiating stuff with these formulas, I felt like it'd be a good idea, that's why there's a bar right here, to just practice why we need the product rule. Let's look at an example where we could do it 2 ways. We'll see how the product rule goes and how it might fail, and we'll get a good feel for why it's suddenly so necessary. So the function I want to take a look at is y equals x squared times x cubed. That's a weird function because if you saw that, your temptation is probably to simplify it and call it x power 5. That'd probably be the good way to go. Well, let's suppose we called f of x, x squared, and g of x, x cubed. And we could differentiate these on their own if we really wanted to. We could say, I'll put a comma here, derivative of f of x, because that's a power function. The power of 2 goes down. The new exponent is just 1, so that becomes a 2x when we differentiate. Likewise, g prime at x, same sort of game on this one. Any volunteers for the derivative of x cubed? Exactly, so we have our 3x squared here. And now I'm going to take these two components, the 2x, let's multiply it by 3x squared, and see what we get out of that. We would get the 2 by 3 for 6, the powers of x, emerge as a power 3. So if you take those two pieces, multiply them together, we get 6x cubed. Now here's the trouble. That is not the derivative of y, and that's really unfortunate. If it was, then our calculus class would probably be 3 credits, not 4 credits. You have a lot of extra work because of these weird algebraic matters. So let's take a look at this from a different point of view. Y also simplifies to x power 5. Now, when you do the derivative of this thing, call it either y prime dy dx, completely up to you. This, the real answer should be 5x to the power 4, not 6x cubed. This doesn't even have the right degree on the answer that we have here. So this is the correct answer. But let's also practice it through the product rule at the same time, just to get a feel for it. Again, we have the right answer. We know the answer is not found by differentiating the components and then just multiplying together. But if we kept the function in this form, it would be y equals x squared multiplying x cubed. Again, think of this as practice. Up here, the format for what we're going to put in, all right, this one is y prime, essentially goes like this. If you like templates, this is a really good strategy for getting fluent with the product rule. Start by writing the product rule where the red dot is, by just putting a derivative on one container, another container where we just copy, plus goes in the middle, then 2 more containers, just these open parentheses, but don't forget the derivative symbol, that prime notation. Next, when we go to use this on functions where we absolutely must, we take the first factor and we just copy it in. Here it goes, x squared, x squared. Go to the second factor, that would be the g function. As x cubed, it goes here and here. And now this process is what actually gives us the right answer. It just looks ugly because, again, that's the best way to do it. This is just practice using our brand new formula. But we can now differentiate everything. Y prime is going to be, first right here, that's going to come out as a 2x. Things I'm just copying, I'll drop the color coding on. X cubed has no prime symbol on it, so it's just times x cubed. Plus, copy in your x squared. Now let's go back to green because we are differentiating this one. This turns out into 3x squared, multiplying. Now, after we use a product rule and what's coming is the quotient rule, we do have to simplify our result. This is going to be y prime equals, first, that's a 2x power 4, plus, this is going to be 3x power 4. Adding those terms together, we do get 5x power 4. As we must, because again, the middle column is the best way to do this process. But it's good to know the product rule does give you the right thing if you differentiate this without simplifying it first. But if you try to differentiate this way, let's put a big warning on this. This is not the correct derivative of y, unfortunately. So the product rule is just something that we have to have if we're going to differentiate functions, not necessarily like this, but functions that cannot be simplified by combining the bases. Well, any questions at all, folks, with how this rule goes down? Okay, this demonstration here is definitely not a proof, but if you're curious on how the proof would go, There's some optional reading right here. Essentially, you just use the definition of the derivative 3 different times, one weird trick that's highlighted in yellow, and you get this rule right back. It's purely optional reading, so I'll always on the Moodle website kind of indicate that. So if you open something that says optional and you don't like it, just close it. It won't affect your grade, I promise. Well, let's take this then. I'm just going to make this kind of walk its way down while we practice this a few more times. Instead of doing x power 5 or x squared times x cubed, its expanded form, we'll do it on problems where you have really no choice. You must use the product rule. And we'll see more of those once we go to sections 3.3, when we add the trigonometric functions. So first one to give a try, I have a list of things that start off nice and get slightly harder as we go. So in black, this will be part A, the actual question. And let's start off with, let me use an uppercase f of x equals x cubed times e to the x. So this is a situation where we have no choice any longer. You cannot combine the bases because the bases are different. One's x, one's base e, which is a constant. So this is where product rule is suddenly required. If you ever notice that you're multiplying functions and you can't combine them, that means we must use product rule. So here's how we're going to start. Let me just recopy the function. F of x equals x cubed times e to the x. So this is where I'm just copying. You could have skipped this step entirely, but a great way to think about this is if you differentiate f, you could call it f prime at x. The pattern of attack always is going to look like this in the product rule. You put down 4 parentheses, plus is in the middle. Don't forget these are really easy to miss. I'll try to emphasize them in these notes because we're getting used to it. But if you don't put the derivative symbol in, it's much harder to use the product rule because it's confusing which one is actually differentiated and which one is copied. Then go to your product, x cubed, you just drop it in this order. So that one portion is being differentiated, and then the other portion is just being copied in. Return to the e to the x function and same game. It'll go here and here. It looks kind of weird with these wide parentheses, but again, this is a pretty good format when you're starting out. If you feel like you get a really good feel for this and you can just see the function, write down the answer, that's kind of the goal, to get to that point. But this is like the essential practice that helps us get to that step. So we can say next, the derivative of f at x. First, we differentiate x cubed. That's a nice application of the power rule. We just get a 3x squared. I'll drop the color coding on anything that's just copied, not being differentiated. So e to the x copies in, plus, and then x cubed. Now we must differentiate e to the x. This one is nasty unless we use a formula. Anyone happen to know how it should go by formula? Yeah, go ahead. Turns out it's not one, but close though. If it looks, say, like this, we would have gotten one in that case. But it's the base e that's making it suddenly a little bit different. Yeah, go ahead. Good call. It's our world's best time, wonderful derivative. It's that one function where you differentiate it, you get it exactly back. That means it's confusing in a certain sense, right? But once you see that trick, it becomes pretty fluent. It's just been a while since we've done that derivative. So differentiate e to the x, no change. You get it right back. Now with what we have here, we do have to simplify our answers, but you know, there's not much to do. There's no like terms. You could factor e to the x, but factoring is not giving me anything extra. You can just leave your answer right in this format. So if you like to factor, I'd say go for it, but not a requirement. That means we did it, folks. This is a nasty derivative if you're trying to work on it directly, but think in terms of a product, apply the product rule, and it was done in just a couple steps. Here's how people sometimes do this once they get lots of practice. They look at x cubed e to the x and they say, well, I'm going to differentiate that first. There it is. Copy that. There it is. Then they'll say next, well, I'm going to put a plus. So we're good. Copy this, throw it in, differentiate that one. Well, we did, and there it is. So that's how people get to once you've done it a lot. But for the starting out, it's good to be methodical because we're just trying to absorb that definition. Sorry, say again. I missed that.
Once you start, you take it, you just get, so, okay, that's the first chapter, and then you just basically take the original one and you copy and paste the plus and then stuff.
Exactly.
And then throw in
Exactly. So that's what we're trying to get to. But once we're learning, this is a pretty good strategy. If you feel you don't need it, not required on the homework. You could just differentiate it directly. Since the way you said it is kind of the goal for these notes, for both product and quotient rule.
it's harder to get back.
It will, yeah. We'll see those in a moment. Any questions at the moment so far? Okay. Well, this one wasn't too bad because it was, just a function with one term multiplying another function coming in as one term. And it can't get too bad just yet until we get the trigonometric functions. Let's try out this one as our second problem. Here's our part B. Put a border to say the last problem stopped, and the next one is starting. And this function will go g of x equals x plus 3x e to the x. This one's a little bit different, right? There's extra things happening. We have a plus sign here. So relative to that plus sign, there is no product rule. We'll use the sum rule to get through that. Then we have a constant multiplying the function x. We're going to have to use the constant multiple rule. Then the function 3x and e to the x are multiplying. They can't be combined. So that's the product rule. Another thing that gets a little bit tricky in chapter 3 is all these new formulas, sure, they're great, but they interact with each other. They intertwine, they go together. So the more rules we put on the table, the trickier they can get once we're using multiple rules at once. And this one's kind of a practice problem at getting there. So if we were to differentiate this one, first let me move this away. The pattern for differentiating, once I find it the home row on the keyboard, there it is first, let's just go right to it. G prime at x will be equal to, first we differentiate that term. Anyone have the derivative of x itself? Exactly, it's just a 1, so there we go, here's our 1. Because we're doing the sum rule, we just copy plus. But now right here is where I would pause. I'm going to take the 3x e to the x and put it in like this. Don't forget your prime symbol because that's the reminder you're about to differentiate. Also, it's a really good idea to write this down. If in your homework you don't put g prime at x, you just give the answer. I mean, I'm not going to be picky and take off credit, but that would become a problem in chapter 4, where we have to look at the function g, g prime, g double prime, and use all three at once to get through a problem. If we're not labeling what's what, it becomes a mess pretty fast. So anything like this, where you're describing the objective, the answer is the derivative, a very, very good idea to get into a habit to, especially for later on in the course. So here's the next thing we have to differentiate. We only use the sum rule, that's why we have a 1. The moment you notice a product, either color code or just indicate some way, somehow, you're about to use the product rule right here. So that's going to be our next step. Does that make sense to folks on this stage so far? Okay, so right here, we'll use a product rule. Let me just put a quick note. Always deserves an exclamation mark because it can be tricky sometimes to even see that there's a product rule in your problem. But once we've identified it, we can now say g prime at x. I'll just use equality going down like this to say it's continuing. It's now 1 plus, and because I'm using the product rule, I'll just do this format. Now back to the function. First factor is 3x, so we throw it in here and here. The second factor is just e to the x, so it goes into this location and this location. Really, we're about done the moment you write down all that stuff. And so the major difficulty of this problem was just getting used to seeing the sum rule together with the product rule right here. But here's what happens next. We'll get 1 plus derivative of 3x. Well, the x becomes a 1, the constant is multiplying, so it stays put. We just get a 3 out. Multiplying e to the x. Then we're over here, so copy in a plus. Copy in another 3x. And now keep this in green because we are differentiating it. It just happens to be itself. So we have 1 plus 3 e to the x plus 3x e to the x. No like terms at all. So that's our answer on this one. And that means we did it, folks. That's the product rule on what could get nasty on here. Now, these can't get too tricky until we have the trig functions in section 3.3. So we'll be doing product rule a little bit more in that section just to practice. Well, any questions at all, folks, on getting through these two here? Okay, so the idea is, I would say right here where I'd be writing these arrows and product rules, sometimes that's the trickiest step. We have to train our eyes to see, is it a sum we're dealing with, so a sum rule, or things multiplying, indicating a product rule. And now, if there is a product rule in algebra, just as in calculus, there's probably a quotient rule. So let's take a look at that next. Any last questions at all, folks, with this first rule? Okay, let's take a look. Here's the good old quotient rule. Actually, let me fix that. It's really important to study the quotient rule. Oh, geez, Control Z that back. With the product rule in view. So let's put this right back where it was. I'll put a little border here to say that example ended. And here's our quotient rule. Let's blow that up as well. I have it in two formats, in Newton's prime notation and in Leibniz notation down below. It's saying the same thing either way. But usually I write it in this format, just like with product rule, if I'm going to use a quotient rule. So now the idea is, if you have two functions, an f and a g, and your objective is to differentiate this kind of setup, where it's f of x over g of x. Actually, I don't want to highlight that way. Let me just do the label f and g. If you ever have to differentiate this, notice how remarkably similar it is to product rule. Your numerator is essentially the same with one difference. And that difference can be massively confusing. So watch out for that negative sign. If you have like a -1 on some of your problems because a minus sign is missing, it's probably because of that right there. No matter how you do this, whether it's in prime notation or the Leibniz notation written down below, notice where that negative sign goes. It's always going to be attached to where the derivative of g is being affected, like right here or right here. Let me highlight that derivative as well. So the numerator, essentially the same, except we swap signs. And there's a denominator to this. It'll be the function g of x raised to the power of 2 altogether. So that's finally the entire quotient rule. On its face, it's not too bad of a rule, but what was mentioned earlier, it can be. Some of the problems can get a little bit difficult. So I'm going to give a hint on one of those problems. It's going to be problem number 27. I'll write it down on the notes when we get to it. First, any questions at all, folks, about quotient versus product rule? Okay, so like we said, it's the same exact pattern of attack. If it's a function divided by a function and you just cannot simplify it, you differentiate f here, copy it here. So f of x goes into 2 spots and g of x goes into 3 different locations in that kind of way, just because it's also squared in the denominator. It's a strange format, and if you're curious, why does it look like this? Our author has a nice little proof. But keep in mind, it's not a proof course, so if you skip the proofs in your reading, that's never a bad thing. Unless you know you're going to be taking lots of math, like real analysis, elementary analysis, you might want to peruse those proofs because they would be coming back in that case. Well, let's give the quotient rule a try and see how it goes. So let's start off with something nice. Let's do a few problems on this because quotient rule is a little bit trickier. But the first one to start out, part A, let's let y equal x over e to the x. So if I put x over x cubed, well, you just want to simplify that and differentiate it in its simplified form. But if it's x over e to the x, this one's not too bad. We'll start by saying the derivative y prime. First, let's say top function, I'll keep in green, or excuse me, blue, forgot my colors. A bottom function, I'll keep in green. E to the x. Oh, shoot, I made a mistake here. Sorry about that, folks. I should have just called this y, is what I was trying to do. Not y prime just yet. That was my mistake there. The reason I'm writing the function y twice is I want it to look like this in black as the original question. Then when we start messing around with it, that's where our solution's really beginning, just to organize the notes. So finally, here's what I want to calculate, y prime. It's always good to be very careful with what's the original function and which one you're actually differentiating. And here's the format this time. I'm going to use the same strategy I did with the product rule and go derivative of something here, multiplying something. Now, watch out for this. For me, this is my most common mistake every time I use quotient rule. I'm tempted to put a plus there, but there is no plus. It's a minus if there's a quotient. So minus goes in that location. Two more parentheses and the primes in the same kind of order you would have expected. So there's our primes. Then in the denominator, put in something to the power 2, and that's our template. If you can write this out each time, then you're in great shape for the quotient rule, because that is the right quotient. Go back to the function. The top function would just fill into 2 locations, here and here. The bottom function, e to the x, will always go into 3 locations. You'll be here copied, here differentiated, and here raised to the power of 2. So that's finally our quotient rule. All we have to do is crank it out at this stage. Any questions, folks, with running through the quotient rule so far? Okay, let me just take a quick screen grab and let's put this down here so we can still keep on looking at it as we go. And here's what the answer would look like on this one. We differentiate x. That's just going to give us a 1 times e to the x. I'll put it here as a paper trail, but if all you copied was e to the x, that's probably the better strategy. This is more for readability if you come back to the notes. Here I have minus, copy in the x, and the derivative of e to the x is itself. It's not super important, but I did want this one in black because we just copied it. And then down below, we do have to simplify this, but the exponent law in this case is exponents like x and 2, they would multiply together. So down in the denominator, we'd have e to the 2x. Any questions so far, folks, to that stage? Okay, here's where it gets a little bit annoying. The calculus is done. So if this was an exam question, maybe it's 5 points. To this stage, I would call it 4 out of 5 points. But we still have to simplify that thing, and it is of great value in chapter 4, I promise. We'll mention it again once we get there. The reason we need to simplify this is in chapter 4, we're often solving this, the derivative set equal to 0, and then we solve for x. Without simplifying the function right here, that could be a bit of a chore. So it's good to get in the habit now, get some good practice in. And here's what happens on the simplification. Nothing special, we could just factor out e to the x. We'll leave behind 1 minus x. And down below, e to the 2x, that's e to the x squared. But you could rewrite it as e to the x times e to the x if it's helpful, just to see the cancellation. There's a cancellation going here to here. So at the end of the day, y prime just becomes 1 minus x. Divide by e to the x. And that's finally our official answer on that problem there. So you might have noticed when we did product rule, we didn't simplify any of our answers because nothing canceled, nothing combined. Sometimes things might, so watch out for that in the homework. If you're doing quotient rule, there's a stronger chance that there is a substantial and worthwhile simplification to go through. Well, that was our kind of a warm-up problem, just getting used to this pattern of attack. How do folks feel about it so far? Does it make sense? Awesome, glad to hear that. Should we try a nasty one next, just for the fun of it? Okay, so this one's the one that I brought to class because it's similar to your homework problem. So I'll put here. This one is similar to number 27. So here's our part B. And in part B, the function is given as f of x is equal to negative 3x cubed minus 1 division by 2x squared plus, oh, hang on. Sorry, folks, I'm copying the wrong one. My finger's on the wrong line. Apologies to everyone working in ink today. It is x squared plus e to the x in the numerator there. Apologies once again. Divided by x squared times e to the x. So that's the one that's actually similar to problem number 27. That's the one we ought to do next. So let's give that thing a try. First, sorry, say again. Yeah, your real problem is the reciprocal of this one. So it's going to look very, very similar as you go through it. I think ours is worse actually, but they're both pretty gnarly in their own way, especially if you're doing this for the very, very first time. Also, notice the conflict of notation. This is indicated as an f of x function, and there's f of x in our formula. So don't think of f as really part of the formula. Think in terms of just the top function versus the bottom function. That's the better way to think about it. And so for our f of x over here, my top function is x squared e to the x. I want to do that on a different line. My top function is x squared e to the x, plus e to the x rather. And our bottom function is x squared times e to the x. So that's the thing we must differentiate. I wrote f of x just to organize the function in color coding, but now we'll differentiate it. F prime at x equals, well, there's a quotient rule here. I mean, it's right there. It's easier to spot the quotient rule sometimes than the product rule because a division bar, I mean, we just see it right away. So if you see that, here's our start. Derivative of the top, copy the bottom, minus the top copied, multiplied by the derivative of the bottom, all divided by the bottom raised to power 2. So that's our pattern. Now grab your top function, it goes into 2 spots. X squared plus e to the x would go here and here. Next, grab your bottom function, goes into 3 locations, the remaining ones, x squared e to the x squared e to the x, and finally in the denominator, x squared e to the x will be raised to power 2. Make sure you have your primes right here and right here highlighted in yellow, and make sure you have a power 2 right there and a minus sign. If you have all those tiny little details, there's like 4 or 5 of them, then you are in good shape for running through the quotient rule. Again, my biggest issue is sometimes I accidentally put a plus. And my next biggest issue is sometimes I forget to square the denominator. If you see me do that, let me know right away and we'll get it fixed. Well, from here on out, it's just differentiation as normal. But one of these 2 derivatives is not like the other. Anyone see which one is the nasty one of the set? Which one amongst the top, the first or the second? I would agree with the second. Do you see what's nasty about that second one? Exactly. There's a product rule right there inside your quotient rule. I mean, this one's not nice either. That's a sum rule right there inside your quotient rule. But I think this one's a little bit worse. So let me put here a little bit of a notation. That's a product rule. This always deserves an exclamation mark because once you see them, then that means you're on the right track. That's half the battle here, is knowing when these rules are coming up. Here's what my strategy is going to be. When I see a product rule on this, I'm not going to carry the whole fraction down. You are absolutely welcome to if you're not opposed to it. But I would probably just take this and do the product rule off on the margin somewhere. Let's try that strategy out and see how we like it. I'm going to drop all color coding. So let's see how this goes. I'm going to take y equals x squared e to the x. So when we go to differentiate that thing, y prime, I'm going to take the shortcut here, but let me know how you feel about it. If it doesn't make sense, I'll put in the extra step that's in the middle. When you do a product rule, first differentiate the x squared. That's a 2x. Then you move over to the other factor and you just copy it, e to the x. Because it's a product rule, we'll put plus in the middle this time. Then copy the first one, x squared. Differentiate the second factor, derivative of e to the x is itself. So there we did it, it's differentiated. And that finally does it, folks. That's the whole result of the product rule right here. But let's pause at that location. Does that application of the product rule make sense to everyone? Awesome, glad to hear that. If you get to the stage where that's the only way you do it, again, that's majorly the goal for these kind of notes. But definitely practice doing it like this at first, just to get the feel for it. Okay, now that we have that, let's go forward with the quotient rule right here. So back to, let me scroll up just a touch, f prime at x is going to be equal to, now I'm going to go left to right, starting in the numerator. We're differentiating this whole thing and we're using the sum rule. So we do need parentheses around that because we're getting two terms as an output. So the derivative will be 2x plus derivative of e to the x, which is itself. And that finishes off this derivative. Here we just copy. There's no prime symbol on it. So x squared e to the x. We don't even need parentheses on it. It's one term. Then minus. Over here, we're copying again, x squared e to the x. But over here, we did the product rule, and this is what we got. So we'll just throw that in. From this location, it'll be a 2x e to the x plus x squared e to the x. Let me put just a fast border around that stuff so it doesn't interfere. Finally, down below, we square everything. This power distributes because we are multiplying these together, so no need to FOIL this time. It's kind of nice. This will be x power 4 e to the 2x. So we've got it, folks, and I forgot my parenthesis here. I'm not picky about that, but it's good to close your delimiters. Yeah, go ahead.
On your x squared e to the x, you put it to x, e to x, shouldn't it be x squared plus ex?
Oh, right here?
Yeah.
Oh, good call. I completely forgot that plus right there. Oh, dang it. That means we have to FOIL too, but we've got to get it in right. So thanks for spotting that. I think I still have enough space if I go like this. And the omission was right there. That should have been a plus. Thanks for spotting that. I'm going to circle this in orange just to make it stand out, or purple, whatever color that is. Other questions or comments so far? Okay, looks like we're back on track. Now, this is the worst part, and part of the reason I brought this one to class. Sometimes there's a lot of work in simplifying these. We have to distribute x squared e to the x on this one, FOIL this out, combine our like terms, and then stuff in the denominator can cancel with our simplified numerator. So some extra steps here, but all just algebra practice. Let's start here. I'm going to distribute from the right, x squared e to the x, first multiplies here. We'll get a 2x cubed e to the x. Then it multiplies here. E to the x times e to the x gives us the e to the 2x, so it's plus x squared e to the power 2x. That finishes off this one. Now this negative sign, that's going to cause some issues when I go to FOIL this out. There is strategies here. I'm not going to take this because it's confusing, especially on the notes. But sometimes if you see a negative here, and you don't want to recopy your whole fraction, you can go like this. Plus, minus, minus. Just distribute the negative inside. Now when you distribute in these negative values, you're skipping that extra step. I'll show it with all steps again, so the notes are massively confusing. And here's what we have to do if we don't do that additional step. Negative goes in, we need a parenthesis, and now we're just FOILing things out. Here to here would be 2x cubed e to the x. Here to here will be x power 4 e to the x. That finishes off that distribution, so we just turn to this one. e to the x is combined, so this is 2x times e to the 2x. And finally, here to here, it's x squared times e to the 2x. Close the parenthesis, and now don't forget there's a denominator, all of which is divided by x to the power 4 e to the 2x. Now it's getting better. All I'm going to do on my next step is distribute the negative sign. So let's get this all copied. 2x cubed e to the x plus x squared e to the 2x. And here's my final distribution. We're flipping all the signs to get negative 2 x cubed e to the x minus x power 4 e to the x minus 2x e to the 2x minus x squared e to the 2x. All of which is still divided by x power 4 e to the 2x. But this is a good place to be in because now we're in the business of cancellations. Let's see what we got. I'm going to look at the powers of x to find the like terms. And we do have two terms involving x cubed and also e to the x. So these cancel off. Now let's go down to x power 2. There's two versions of this potentially, one with the power 2x. And yeah, it's the only one version actually, because e to the 2x appears on both of these. Those are also like terms, so that's gone. It's kind of shaping up a little bit better. Looks like these are the only survivors right here. Negative x4 e to the x, negative 2x e to the 2x. Those don't combine, but they simplify with the denominator. So here's our next step. With the lone survivors, I need to find the greatest common factor, and then we need to factor that out. Anyone see what the greatest common factor would be amongst these two survivors here?
X.
We're going to take out an x and e to the x. Good call, folks. So we'll take out x e to the x. Now divide x and e to the x here. We'll just get negative x cubed. Divide x e to the x here, and we'll get, let's see, 2 e to the x minus 2 e to the x. That look all right to folks so far? Awesome. Then down below, here's the reason why we did this. We have x power 4, and just for ease of cancellation, you could factor that as x times x cubed if you like. Not required. You could cancel and just write down x cubed below it. It helps a little bit more with this e to the 2x. I mean, it just looks kind of funky in that format, but it's nothing but e to the x times e to the x. Here's our last cancellations. Those x's are gone, and the e to the x is gone. That negative sign can just leave inside in the numerator. You could factor out to way in front of the fraction, but those are all stylistic choices. So I have no preference one way or another. I'll leave the negative up in the numerator. So negative x cubed minus 2 e to the x, divide by x cubed times e to the x. So finally we did it, folks. That's the end result on this one. This one was meant to be kind of a nasty one, just to show how sometimes if this is your function, it's not always just the quotient rule. It could be other stuff like a product rule sneaking inside. But also notice, in a lot of ways, this right here is almost like the easier stuff. And all of this below is the grungy algebra, where if you do it too quickly, even if you have great knowledge, it's easier to make a mistake down there as opposed to up here, which is always kind of weird about this kind of stuff. There's always value in this simplification because this could have been an application where you're trying to maximize or minimize. The first thing you would do is take this derivative and set it to 0 to find a minimum or a maximum. So this is work we'll return to in chapter 4 for sure. What we did, folks, this is the major things I want to cover. I do have 2 additional topics. One is summary of all the differentiation formulas. And example 3 is pretty similar to a homework problem, so I feel like this is one we definitely should do. After which, I just have a couple of fluff problems. Here we're calculating a first order derivative and a second derivative on this thing. And if we have time, we have a pretty interesting application. Chapter 4 is entirely about applications, so we'll be seeing this kind of stuff before. That's going back to physics. And the goal is to show if momentum is constant, Force is mass times acceleration, ma. But when you study physics, it really starts here. Force is the derivative, rate of change with respect to time, of momentum times velocity. Really weird, and it actually turns into this if your momentum depends on time. So those are our last topics. I feel like for sure we should do this one because it's on the homework. Well, any questions, folks, before we start this one out? Okay, so what's going on here is it's just a summary of all the differentiation formulas we've seen so far. I've pretty much copied this verbatim out of the textbook. Just a reminder, if you differentiate a constant, you get 0. We have the good old power rule here. This one is like a superstar we use repeatedly. Exponential function, the common ones here. And these are the nice rules. The sum rule, the difference rule, the constant multiple rule. And those are just the newcomers. Here's the product rule and quotient rule. Now there's no f prime at x. Sometimes we indicate a formula by just naming the function and naming the derivative, the copied function in this kind of way. But if we go to calculate, we will put in the of x, but this time it happens to be a constant. So here's how this kind of problem goes. It's honestly more about accounting in a certain way because we have to account for all of the function and derivative outputs here, as well as the format of the function and the inputs we're throwing in. So think of this problem as its main takeaway is just practicing quotient rule again. That's the major thing we're trying to do. So if you saw this, it starts off by writing the derivative of the top at 3 this time, copy the bottom at 3, so just g at 3. Because it's a quotient rule, anyone recall the next sign? Is it going to be plus or minus?
Minus.
Good call. That one is always minus. And think of, if you see a division bar for quotient rule, that's a reminder of you have to have a negative there in the numerator. Then it's going to go f of 3, multiplying the derivative of g at 3, divided by, oh, that's the wrong color. Maybe it's not wrong, it just look weird. Divided by the function g at 3 to the power 2. Here we kind of did it blind, but that's the value of this formula. If you put that on your notes ahead of exam 2, I mean, that's really powerful stuff. That's all you need to get started on this problem and all the others. After you get to here, to me, this is kind of confusing because you have a derivative output here and here. So we just have to be extremely careful when we plug in the results. I think this is the easier step and the evaluation is the trickier step. So let's get these in exactly. First, it says the derivative of f at 3, so we're throwing in a factor of 2. Next, it says g of 3 here, so we're throwing in a factor of 5. And honestly, without color coding, I'm much more prone to make a mistake on this because my eyes just get confused. There's just a bunch of stuff floating around. But if you are a fan of color coding, you can bring these to exams as well. It definitely helps the eye track what's going on, what's going where. So next, g of 3 comes in as a factor of 5, minus, here f of 3, we'll throw in a factor of -4, and g prime at 3, we'll throw in -4 again. That solidifies our numerator, so now for the denominator, we're going to take g of 3 and square it. I'll just start with the output squared. Look up g of 3, it comes out as a 5. And we're through the nasty step. All we have to do is crank this out. It'll be 10 minus 16 over 25. So -6 25ths. And we did it, folks. That's running through the quotient rule in a strange kind of problem. We don't even know the function. We just know outputs at a point and a derivative at a point and nothing else. But they are differentiable functions. Then that's what the result has to turn out as. Any questions at all, folks, on running through this one? Okay, let's try it again then. Here's part B. F times g prime at 3. Well, because it's multiplied, we're definitely dealing with the product rule. So take a look at this formula right here. It will run as first f prime at 3 times g at 3. And then if you track this sign, then that's one of the key differences going from the different rules. Product rule has plus right here and no denominator. Next, it's going to be f at 3 multiplying g prime at 3. So because both functions were multiplied, that's our result here. And same business, we'll just go up above and put in the output. Does that look right to folks so far to that stage? Okay, let's go forward then. Next one is going to be f prime at 3 comes out as a value of 2, so let's throw in a 2. G at 3, I already forgot, it comes out as a 5, so 5 goes here, plus in the middle, then a -4 for where f of 3 is. And last thing, g prime at 3 here, we go to look it up, it's a -4. At this stage, we're pretty much done. This is 10 plus 16. So we get 26 altogether on that result. So they're wildly different answers, but we should expect that to be the case because dividing functions versus multiplying, we always expect different functions as a result. It'd be a coincidence to get the same thing out. Well, that's a process, folks. Again, the major takeaway of these notes is knowing how these work, how to produce them. And we'll be using quotient rule, product rule very carefully, pretty much through the rest of the course. In particular, the next few sections, we'll be hitting it pretty hard as well. So there'll be loads of opportunities to practice. Any other questions at the moment with this so far? Okay, then I do have a question for folks. We have a good amount of time. We can finish off this one. This is a decent application of product rule, quotient rule. It's purely mathematical. Or we could try the physical application. Any volunteers for one or the other? So your homework, as far as that goes, this, we'll probably see it again and run through it in chapter 4. So probably this one's more helpful. Should we try this one then, folks? All right, let's give this a try. If you're ever curious about the applications we skip, just see me after class or send me an email. I'll post the solution. I'll always be happy to do that. But let's give this one a try. We have a function just defined as y equals a function of x on the right-hand side. And this one wants us to do two things. We want to do y prime and y double prime. So first, let's calculate y prime. I'm going to write my answers this way, but I'm putting this step just as a reminder. That's saying the same thing, dy dx. So that's an optional step right there. We'll go to the y function, and it has problems, so I'm going to rewrite it as y equals 3 minus x squared, that's our first factor, times e to the x, our second factor. Right away, this one's turning into a product rule we have to run through. So let's go carefully with this. If you're a fan of running through the shortcut, then I'd say give it a try. Well, no harm in being a little bit more careful on this one. So we're taking the derivative. Take your first factor, 3 minus x squared. It goes here and here. Really, the nice thing about this is, again, it's very similar to quotient rule, with the two key differences, the minus going here and the fact that there's a denominator in quotient rule. The way we copy in things is very, very similar. E to the x is just going into those remaining locations. And the main takeaway is there's two things being multiplied, or 3 or 5 things being multiplied. We just write down as many terms as we can so that the prime symbol moves to each one of the factors. Move your prime over on every factor, then you always have the right product rule. Well, we don't have any problems with like 5 different factors on product rule, but that will be coming on the next section. So we'll see how to extend our product rule coming up. But first we have to get through this. It's not too bad. Anyone see what the derivative is for what's highlighted here in blue? Close. The problem is with the 3. Yeah, because it's a constant, that one will go to a 0. And it'll be 0 minus the 2x, like you said. So that'll be our first piece. Next, e to the x is copied in. Plus in the middle. 3 minus x squared right here gets copied as well. And then we differentiate e to the x. Always a little confusing until we're just familiar with that being the most wonderful formula for differentiating ever. Just a copy. So now that we got here, well, that's y prime. And what you could do is dive down to y double prime right here and now. But that's not always the best strategy. If you're taking a multiple derivatives, you probably want to simplify this a little bit more, just so that your next steps are a little bit easier. Yeah, go ahead.
Where it says, 0 minus 2 to the x, you also just say negative 2 to the x?
Yes, absolutely. That'd be terrific. Pretty much only put in the 0 just to emphasize it on the notes. But if you simplify those kinds of things in the middle, I think that's wonderful. Other questions so far? Okay, so let's simplify this a little bit more. First thing I'm doing is, just like you're saying, dropping that 0. I'm gonna write this as negative 2x e to the x, 3 minus x squared, or excuse me, plus 3 minus x squared e to the x. Now, if we were to differentiate that, there's one product rule there. There's a second product rule here where the parentheses are. So I would propose an alternative strategy. Let's factor out the greatest common factor of e to the x to see if we can reduce the number of times you have to do a product rule on this thing. Sometimes simplifying makes a tremendous amount of difference in the amount of work you do to differentiate. And the more we practice, the more you'll see where the right simplifications are. So factor out e to the x, I'll factor it off to the right. That'll leave you a negative 2x plus 3 minus x squared. Here's e to the x factor to the right. That looks weird the way it's written because the terms are out of order according to degree, but there's no harm in that. If you left it like that, that's totally fine. I think I have a psychological need to make x squared come first, so I'm going to rearrange it. Negative x squared minus 2x plus 3 times e to the x. That's slightly easier for me to work with. Now we're ready for y double prime. Sorry, go ahead. Oh, I gotcha. Kind of what happened was, we take a look at this right here, or I'm on the wrong line. Let me take another look. We take a look at this portion right here and we expand it. It would go like this. Negative 2x plus 3 minus x squared e to the x. We distribute it back in and put parentheses around that one. We would get negative 2x e to the x from there to there. We'll also multiply to this one, so plus 3 minus x squared e to the x in that kind of way. So essentially what I did was I took this and just factored it out. It left just the negative 2x here and the 3 minus x squared right here. Does that make sense visualizing it that way? Awesome. Thanks for asking about that one. Sometimes the factoring definitely just looks different, especially when you have weird functions. We'll be seeing the trig functions coming up next. Other questions at the moment? Okay, well, we've got 4 minutes and one more derivative. Let's see what we could do with this. Now we're doing y double prime. So this one here, I would write the step as y double prime equals. This step is optional just to indicate what it looks like in Leibniz. It'd be d2y, the second derivative of the y function, with respect to the variable x twice. So notice the 2 goes here between d, derivative, and y, the function. But here 2 goes by x because we're differentiating with respect to x both times. But at the end of the day, y double prime is saying the same thing. It's just saying redifferentiate that function. Well, it's a whole new product rule. That's going to be my first factor. That one will be my second factor. So if we go to differentiate this, let's see if we can get some parentheses in first just to help us out. So that right there is our product rule. Let's fill in the blanks. In blue, we'll put in negative x squared minus 2x plus 3. And then one more time. Then in green, I might have made these parentheses a little too big, but that's okay. I'll just go into the remaining slots. Finally, we go to differentiate. Anyone have the derivative for the blue portion here? Good call, absolutely. We'll get negative 2x minus 2, just a minus 2 because the power is 1. Derivative of the constant, because it's being added on, just goes to a 0, so we don't even need to record it. Then from here, copy an e to the x, plus from here, copy in all that stuff. Negative x squared plus 2x plus 3. Finally, differentiate e to the x. There we go, we did it. There's its derivative. And now when we look at this, you might wonder, is there cause to simplify it further? If we did anything extra, could we cancel stuff, combine like terms, and so on? Take a look. Turns out we could. If we factor out e to the x one more time, negative 2x would combine with positive 2x. That means we do have cause for simplification. We must do it. So here's our next step. Just like before, I'm factoring out e to the x to the right. That means this e to the x is gone, and we copy in the guts, minus 2x minus 2. Over here, this e to the x is canceled off. We copy in these things. It's going to be minus x squared plus 2x plus 3. Last thing to do, folks, and we just about have it. Combine all of those like terms. I'll go and order the, oh, sorry, question first. So negative x squared plus, oh, I forgot the sign. I put in a plus. I should have recorded a negative. Thanks for capturing that. Well, they put that minus there. Sorry, missed your question about the other idea, but that was what I missed right there. Thanks for spotting that. Somehow I thought it was a plus when I went to copy. See where else it affects. Affects that slot right there as well, right? That should be a minus. Then let's keep on tracking this. Down to here, that was a minus as well. So minus 2x in that location. I think we're definitely in better shape. Does that look all right to folks so far? Awesome. Well, last order of operation or last motions to go through. Negative x squared copies in. And they don't cancel, but they still combine. So our simplification was worth it. That's a minus 4x's. And then negative 2 plus 3 will give us a plus 1 times e to the x. We did it, folks. That's the second derivative of that function. See if we can show the whole problem possibly. Yeah, kind of sort of fits. And that's the process. Well, any last questions or comments so far, folks? Yeah, go ahead.
What is the second derivative used for again?
If we say our function right here is a position function, the position from a starting point with respect to time, y prime would be velocity, and y double prime would be the acceleration of that object that's moving in one dimension. So think of first derivative as velocity, second derivative as now acceleration. Other questions so far? Yeah, go ahead.
When you write the notation for the second derivative, would it be like, would it be more correct to write it like that's the second derivative of the top function?
Second derivative of this right here?
Yeah,
It essentially is, absolutely.
and so like down below, would it be just yes, and y yes?
Right here?
Yeah,
Well, it should be d2y because this y right here is that function there. But you could have wrote this as y double prime is also the derivative of y prime with respect to x. That would indicate it as well. Is that the kind of question you're asking about this thing right here?
yeah, just because like the saw this like way out of context, I guess, and we weren't working down, and it would just be us taking the first derivative of that function, but it's only because we do that.
Yeah, so right here, y double prime, it's differentiating that, but y double prime is also saying you're differentiating the derivative at the same time.
So it's just.
Exactly, yeah. Yep, you betcha. Other questions so far, folks? Okay, well, have a great night, everyone. Again, I'll send out a mass email just as a reminder. And this is unusual. I have a scheduled conflict of Thursday, so I won't be in class that day. Sorry about that, folks. I'll still have office hours 4 to 5, so you're definitely welcome to come by. And if I did get your exam back, I have it down here.